Okay, hi everyone. So thank you very much for having me, and it's a pleasure to present here with these two great reviews of old and recent work. And I'm going to present my work that tries to get at the question that Nathan started with, that there's all these interesting markets that we would like to understand in real life, and we can't actually even agree on what would even happen in them. So I'll try to give one explanation of what could happen. And the way that I do this, and I was talking to the organizers, is that because this is a recent paper that I'm working on currently, I'll pretend that this is a typical presentation that I would give with a bunch of other papers that people are doing right now. And then towards the end, I think I'll go and try to think and be a little bit more thoughtful about the big picture of how we're trying to accomplish this, of understanding how these markets actually work and how public policy can work in these markets. Adverse selection is a big problem in many markets. And governments already intervene in these markets in many complicated ways that we did not talk about. But besides doing things like what Jason was suggesting, like mandates forcing everyone to purchase insurance, governments do other things like community rating. So forbidding firms, limiting how much price discrimination firms can do. Governments implement risk adjustment payments to firms, which are these complicated subsidies that Glenn was talking about. There are different subsidies for different groups of consumers. We regulate contract characteristics. And so when we think about almost all of those policies, basically all of them affect contract characteristics, what kinds of contracts are going to get sold. And often the whole point of those policies is to affect what contracts get sold. So if we want to understand this, we have to understand how menus of contracts are going to get transacted. But like Glenn was saying, one thing that we can do is that we can try to be very simplistic about what kinds of contracts are sold. And we have these nice supply and demand models that are actually very tractable. But like Nate was saying, the models that don't do this have all these problems that we don't even have a prediction of what would happen, except for the case that, so Nathan has this very interesting evidence of many markets that seem not to work because nothing is transacted. So all that I want to do is that I want to have a model that where the characteristics are going to be endogenous. So I do want to predict what's the menu of contracts that will be traded. But like we've seen that is very important in the data, people can be heterogeneous in more than one dimension, and an equilibrium always exists. And what I'm going to do is going to be extremely simple. So all that I'm going to do is that I'll take this standard model of when there's only one type of contract, and that we just do supply and demand. And I'll apply that to the case where potentially there are many contracts, and we want to let the contracts fight it out within the model and figure out which ones are going to unravel and which ones are going to be traded. So you just go back to the picture that Glenn showed. Had we a model with a single contract, we could draw the supply and demand curves that tell you at any given price, what's the quantity of people who would buy each contract. That would be this demand curve. Now, with adverse selection, I know that if that there's also an average cost curve, which depends on prices, because for example, at this quantity, if I take the Q people with the highest willingness to pay and have them purchase insurance, they're going to have a cost that's going to be different than some other set of people. And equilibrium is given by the point where the supply and demand cross. Now, more subtly, this model also tells us when the market's going to unravel. And so what I'm going to do is that I'm going to use the model both to tell me what prices are and to tell me whether some given contract is going to unravel or not. So this is an example where the market unravel, because like in Nathan's work, average costs are always higher than the demand curve. So that's all I'm going to do. And a preview of the kinds of things that we can say, I'll calibrate an empirical health insurance model. So this picture is being generated by a lot of consumers that actually have many dimensions of heterogeneity. So these guys have moral hazard. They have different probabilities of having a health shock, different risk preferences. They differ in all those ways. They're going to purchase there's going to be a bunch of contracts they could purchase that give them from 20% coverage to 40%, 60%, and potentially full coverage. And then what I'm going to do, for example, is that I can see, so the red bars are going to be a histogram of what they would purchase if I don't intervene in this market. The silver bars, I'll implement a mandate, so this very common policy of forcing people to buy some bronze plan. And if I didn't have an equilibrium model, I would get that everybody would, everybody who was before buying less than 6% would buy 60%. If you were buying more, you would stay exactly unchanged. And what's going to happen is if you have an equilibrium model is that we see that it's not what's going to happen. So there's going to be some important unintended consequence here, because when I put all the cheap people purchasing 60%, that creates a huge incentive for the people who are purchasing more than 60% to try to be pulled with the cheap people at 60%. So I'll come back to this picture and explain it better. What I want to do is that I want to explain the model, and that's a single slide, so the model only has one slide. And this is a great time for clarifying questions, because I don't want to go off talking for half an hour and by myself. So the way the model works is that there's consumer types. So theta is a consumer type in some set of all possible consumer types, capital theta. They're distributed according to some probability distribution mu. There's a set of contracts X. So X a contract, cap X a set of contracts. And agent theta has some utility function, which depends on which contract he buys and how much he paid for it. And there's some cost of supplying the contract to the agent. So that's the model. If no one, does anyone has any questions? Or okay. And by the way, it should be clear that we can model basically almost everything that we talked about before that doesn't involve imperfect competition. This is going to be a perfectly competitive model. Just with this. So for example, the Akerlof model would be the case where the set of contracts only has two things. Either you buy insurance or you don't buy insurance. So if cap X equals 0, 1, that's the Akerlof model. The Rothschild and Stiglitz model has a more complicated set of contracts. It could be any number between 0% and 100%, but there's only two types. Either I'm the guy who has a low probability of crashing my car or a high probability of crashing my car. Yeah, actually theta and X are actually potentially infinite dimensional and potentially not even dimensional, and that they don't have to be vector spaces and so on. But in the talk, you can think about this as being something RN. Yeah. So it could be your risk aversion and your probability of crashing the car and so on. Moral hazard. Nate?
You want to motivate the separation between P and X? Because, if I understand correctly, it's going to be different, right, if you think of P as deductible versus if you think of it as the price.
Yeah.
It's going to get different equilibrium predictions.
Yeah. So the way that I'm going to write this is that X specifies all the dimensions of the contract except for the premium. Right. But then you're saying, it would be interesting to think about a model where you specify all the dimensions of the contract except for the deductible.
Or other characters. So
there's
something special right here about the price, right? Because it's what you're separating out. And that's the deviation with the Rothschild-Stiglitz prediction. So I'm just wondering, what is it?
That's a good question. I don't think it matters, but I would have to stop and make sure that it doesn't matter. And actually, I should probably prove that it doesn't matter in my paper.
Okay, so your intuition is that it's only that it's single.
My intuition is that it doesn't matter. Well, it's just that I want to parameterize the contracts in some way. Yeah, my intuition is that it doesn't matter that price is going to be different. But it's easier to understand. It's definitely going to make it a lot easier to understand. So the way that you should think about it is that X specifies my deductible, my copay, my out-of-pocket maximum, but not the premium. The premium is going to be the price, which is separate. Does it make sense? But I guess we could have had the price, the premium be something, and let the copay adjust. And my conjecture is that it's the same.
I think I'm with you. Like the single dimensionalness is what's going to get the equilibrium, and you can put it on other dimensions. If you get multidimensional multidimensional prices.
No, I don't think so. I think the multidimensionalness doesn't matter. We can talk about this later. Yeah. Okay. Okay. And so, so this includes all these examples in the literature, like we just said, including most recent applied work. So in the talk, I'll just say that utility is quasi-linear. So my utility is actually for buying contract X at price is P. It's just some willingness to pay that I have, U of X theta minus P, the price that I paid. And I'll assume that U and C are continuous and so on. It's just some definitions that we're going to use. So a price is going to be a measurable function, P, that tells me for each X, for each possible contract, what's the price of that contract. An allocation is going to be a measure over the set of types times the set of contracts that tells me who is buying what. So you can think of alpha of theta X as being the number of theta agents who are buying contract X. And of course, if I add up how many theta agents there are in the allocation, that has to add up to how many theta agents exist. And the price allocation pair is incentive compatible if almost all consumers are purchased in an optimal bundle according to alpha. You should not focus too much on the almost all every, That's only there because when you're talking about measures, it only makes sense to talk about things almost everywhere. Yeah.
Curious,
Mm-hmm.
because it looks like the way you define this alpha,
Yeah.
there might be multiple players, like type beta, buying
Different things. So the nice thing about theta, about defining the alpha like this, is that it could be that half of the Mr. A's are buying contract 1 and half of them are buying contract 2.
But I thought theta was the only thing different about them.
Mixed strategy.
Yeah.
I see.
Yeah, and that's going to be important. An equilibrium wouldn't exist otherwise, always. Yeah. Does it make sense? And because we're going to care about selling people contracts and the companies making money, so we care about the expected cost of people who buy some contract. So I'm going to use this notation, EX of C, for that all the time. So EX of C is the expected cost, according to alpha, of everyone who's purchasing contract X. Okay, so now I want to define a competitive equilibrium. So what I want to do is that first, I'll try to define a very naive notion of what a competitive equilibrium would be. I'm going to crash and burn, because there's going to be too many of them. But then we're going to do a little bit better and come up with a good definition. So the first definition that I could come up with of what a competitive equilibrium is would be, look, it's a price allocation pair that it's incentive compatible, everybody's maximizing, and all firms make zero profit, so price is equal expected costs. And of course, it has to be true almost everywhere because conditional expectation is not defined everywhere. So if there's some contract that's not being sold, this is actually not putting any discipline on what the price of that contract is going to be. Here's an example to clarify that. So this is going back to Nathan's example of the Rothschild and Stiglitz model. So now I put in the x-axis the contract that I'm purchasing, which is going to recover some percentage of my loss. So there's a contract that covers 0% of my loss, 10%, and so on, up to 100%. And in the y-axis, I'm going to put the price of the contracts that I'm purchasing. So the Rothschild and Stiglitz original equilibrium had all the high types, or the people who are more likely to crash their car, purchasing full insurance. So that would be this H ball up here. That's what I represented here. It also has all the lower types purchasing some lower level of coverage, which I wrote down as this L ball here. And both of them are paying actuarially fair prices. So this price is set so that the firms make no money. This price set so that the firms make no money. Now, ICH is going to be the indifference curve of the high types. So that means that the high types are indifferent between H and any of these contracts. And ICL is the indifference curve of the low types. And what that means is that this black curve, P of X, along with this allocation, is going to be an equilibrium, because nobody wants to buy anything else if those are the prices. Now, that seems like a reasonable solution, but the thing is that there's many other equilibria, and not all of them are going to make as much sense. So for example, this would be an equilibrium. But in this equilibrium, I just changed the price of all the contracts that are not being sold, and nobody wants to deviate because I only raised the prices of different things, so nobody wants to deviate, so that's an equilibrium too. You might say that this one's not as reasonable, because if some firms enter the market for this contract, it would drive the prices down, but it's an equilibrium. Now, just like this is an equilibrium, at least this one has the same allocation as the equilibrium that I started with. But there's going to be many other ones that have different locations. So for example, it could be that no one purchases insurance and nobody sells any insurance because they think that only really expensive consumers are going to show up. It could be that everybody purchases 50% insurance and nobody sells any other amount of insurance because they think that people who show up are really expensive, and even at zero, people would be really expensive. So there will be too many equilibria if we do this, and what I want to do is that I want to refine the set of possible equilibria somehow. Okay, so the way that I want to refine this equilibria, there's two ways of thinking about it. So the first way is that I want to figure out intuitively which markets would unravel. And the second way, which is more similar to how the math works, is that I'll use a standard trick from game theory, similar to, for example, proper equilibrium, that I'll introduce full support in this somehow so that I get rid of all these paradoxes with taking conditional expectation sets of measure 0. So what I'm going to do is that I will introduce a perturbation, which is going to be, I'll take an economy that looks exactly like the original economy, but instead of having every possible contract from 0% to 100%, I'll have some finite number, let's say 100 contracts. And at each contract, I'll add a small measure of crazy guys that always buy that contract and are really cheap to cover. So formally, a behavior type X, an agent who always purchases contract X, a perturbation X bar eta is an economy with a finite set of contracts X bar, and a small measure eta of these behavioral types. And there's a positive mass of them in every contract. So what that does is that now this is going to be an equilibrium of a perturbation. And moreover, there's not going to be any equilibrium of the perturbation that look like this crazy equilibrium that I had before. And the reason why is pretty simple, because if I go to a perturbation, so there's this finite set of contracts, it could never be that the price of this contract, for example, is some really high price, because then only the behavioral types would purchase that contract, and then the price would be 0. But then as the prices go down, so if I had a price that was high, as the prices go down, eventually prices would hit the indifference curve of the low types, and then all of the low types would flow into buying this contract. But the only reason why they would decide to buy less insurance to go from here to here would be if they're making money on the firms, if the firms are losing money, given that the firms are breaking even here. So the firms would actually lose money if the price goes down. So what would happen would be exactly like that Akerlof death spiral in the one-dimensional model. So there's two ways of thinking about why this is reasonable. So one is that these Akerlof death spirals are disciplining that not too many of these contracts are sold. And the other way of thinking about it is that we're using this standard trick in game theory to get rid of the paradoxes related to measure 0. Now, of course, if I just do this finite, particular perturbation, this market didn't completely unravel, because the reason why the prices are still high is that in the perturbation, there's a tiny measure of these L types that are still buying this. And so the real equilibrium definition is going to be that I'll just take a larger and larger set of contracts that's filling in the 0-1 interval, and then and a smaller and smaller total measure of these behavioral guys. And then equilibrium is going to be anything that's the limit of equilibrium in these perturbations. So I'm not going to do the math for those definitions. I'll just show you that in pictures. So the real definition of an equilibrium is going to be that we have a perturbation like this. Let's take finer and finer perturbations. So here I just increase the number of contracts that I have. I reduce the total mass of these behavioral guys that I have. So you can see that as I flicked from this slide to this slide, the blue ball actually grew a little bit because I don't need as many of the L types to be over here, keeping the prices high. And so if I keep going, I'll end up with something like this, which is what we had in the first place. And indeed, in the Rothschild and Stiglitz model, this is going to be the only competitive equilibrium according to my notion, which leads to an interesting question of whether this is the only thing that we think is reasonable, but I guess it's something that I'll talk about in the end. So that's how the equilibrium works. You seem to have a question.
Your example with the ridiculously funny prices before.
Yeah.
I guess I don't find it sufficiently motivating for
Yeah.
me to add these behavioral agents.
Mm-hmm.
And I imagine there's a more complicated situations that arise, which this actually generalizes to do the right thing there.
Mm-hmm.
Because like in that previous example, I mean.
Yeah, you could have by eye, you could have figured it out.
Exactly.
Yeah. I think the cases where are really interesting are the cases where we had no idea of what an equilibrium looks like. I'll show you one of those soon. Yeah, I'll do that next.
So the point is this sort of behavioral perturbation lets you focus in much more broadly on what the right equilibrium is.
Well, it gives you one possibility of what the right equilibrium is, and then I'll try to look at it in more interesting cases now and see if it's telling me something interesting. So I'll take like a Milton-Friedman approach of I'll not judge the model so much by the assumptions right now. I'll do that in the end of my talk, and then right now I'm going to judge it by the results. So let me show you, I guess. So I guess one thing that's nice about this approach is that an equilibrium is always going to exist. So because the Rothschild and Stiglitz model chokes, because this model could tell you that the equilibrium is for nobody to buy anything. That's perfectly possible. And because all the standard models are particular cases, so all the cases where Nathan showed that nobody buys anything would be cases where nobody buys anything. But this model never chokes in that you never ask the model, oh, what's the equilibrium? And the model just says, oh, sorry, I don't have an equilibrium. I don't know if people buy nothing or if people buy something. This one's always going to tell you something. So an equilibrium always exists. I'll not go into details about this, but it always exists. You could give strategic foundations to this model, so related to the literature that Nathan was talking about. So, I reverse engineered some strategic game that explains this model as a strategic equilibrium. And maybe I'll explain this in the end of my talk. What I'll do instead now is that I'll use the last 2 minutes that I have to just take this model for a spin and see what this equilibrium actually look like in cases where I actually had no idea of what an equilibrium could even be. Let me do that. And so actually, I'll try to answer Jason's question from the first talk of what happens if I get rid of the IR constraint. What happens if I make everyone buy 60% insurance, for example. So I went and I took a nice model, an empirical model of health insurance. And this is kind of a reduced form of this model that you get under some parametric assumptions. But basically, it's a model where I can have a health shock. I then decide how much to spend on healthcare. I'm risk averse. And so people differ in several things. So people differ in their expected loss. People differ in how much moral hazard they have. People differ in their risk preferences and so on. And so the reduced form looks like this. The willingness to pay that I have for a linear contract that covers me on X% of my loss is going to be X times M, which is my expected loss, plus some term that is increasing in X squared over 2, times H. That's a moral hazard parameter that I have. And both the expected loss and moral hazard also increase the cost to the company of insuring me. But the moral hazard costs to the company twice as much as I benefit from it in dollar terms. And there's this insurance term, which is also increasing in X in the 0-1 range. And it's multiplied by the variance of my healthcare shock and my absolute risk aversion. And so I just calibrated these numbers to be similar to what they find in their study of a large US employer. So for example, this average loss was $4,000, and the standard deviations of losses were like $25,000. And because this is a 4-dimensional set of types, I just assumed the types had a log normal distribution, and they had a log covariance matrix that's similar to what they found in their paper. We explain more details of calibration there. So so the first thing that you could ask is, okay, so what's an equilibrium going to look like? So it's going to look like something like this. So we have the black line shows you the prices from 0 to 100% coverage. So for example, 20% coverage must cost like $700. 40% coverage must cost almost $2,000, and so on. Just the fact that this line is convex already tells you that there's a lot of adverse selection, consistent with what they found in their data. The fact that, so these red balls is that I wanted to plot the quantities, not just the prices. And so the size of the red balls is proportional to how many people are buying contracts in each range. And I wanted to plot adverse selection, at least one measure of adverse selection. So the height of the red balls is proportional to the average loss parameter of people buying each contract. So people who buy higher contracts have much higher expected losses. So that's what an equilibrium looks like. Here's, if you plot each consumer as a dot, if you plot their average loss and their average risk aversion, we can see how they're sorting across different contracts. So red means that you're buying more insurance, blue means you're buying less. So you can see that they're sorting like we would expect, but there's still a bunch of red dots here, for example, and that's because I plotted 2 dimensions of heterogeneity, and actually there's 4 dimensions of heterogeneity. Now I can try to answer Jason's question of, if I don't have an equilibrium model, I could think that if I impose a 60% mandate, then all these people would purchase 60%. What actually happens is that all the cheap people purchase 60%. That's this huge ball here of a lot of people purchasing 60%. And actually, these are 85% of people, which is more than people who were purchasing this before. And the reason why is that when all the cheap people purchase 60%, if I'm a person who is doing slightly better, that creates a lot of incentives for me to purchase a little bit less insurance. You can show that in equilibrium, the prices are going to be continuous. So what's going to happen is that a lot of people are going to reduce their coverage, but in the end, we end up with these continuous prices. And lower prices for everyone. So these people actually benefited from all the cheap people who came here. Of course, social welfare goes down because we already had all this adverse selection, so people were buying too little insurance. And then this is going to only make adverse selection worse in the intensive margin. But those people are better off because they face lower prices. Okay, so the last thing that I wanted to explain is that I wanted to use this model to explain why these markets are inefficient, why people are going to be making inefficient choices in a competitive market, why is there market failure. And I wanted to give a very brief explanation connecting to the previous AGT workshop that we had on public finance on what kinds of interventions we might look at in these kinds of markets. So I'll use two definitions. Yeah. Mm-hmm.
I've forgotten the assumption that you're making that you see some equilibrium or before the given timing. What's the difference?
So the difference is this is a price-taking equilibrium notion. Does it make sense?
So it's still a competitive equilibrium.
Yes, but it's not like a Nash equilibrium. So if you go back to this example, to the Rothschild and Stiglitz, so we ended up with this equilibrium. So it could be that the firms could make money by offering a lower contract here. But it's still a competitive equilibrium because everyone's making zero profits and the consumers are optimizing, taking prices given. Does it make sense? So that's the key. There are strategic games that you can do to cook up this as an equilibrium, but they're going to involve making assumptions like firms have limited capacity and they can't turn consumers away, so they can't go and do this deviation here. Does it make sense? Yeah. I'll
Kind of like
yeah.
what he was saying at the end to get back to equilibrium. Right?
Yeah, it's very similar to O'Reilly logic, right? That somebody else is going to add contract and drive the price down.
Yeah.
So then you get the O'Reilly. This is
Yeah. I'll actually explain this in detail because I think there's a deeper.
In the multidimensional case, I actually carries it as O'Reilly. If it's O'Reilly equivalent.
Well, I want to talk exactly about that actually.
Question, do
Yeah.
you have anything to say about uniqueness?
I do. I know that it's not unique. I know that you kind of eliminate this rampant multiplicity that everything's in equilibrium.
No,
but
with the,
yeah.
even with the perturbation thing you do, right?
It's not unique.
Right. So
Uh-huh.
do you have any sort of preference domain for which you can say you can have uniqueness, like
Yeah.
Stiglitz kind of context?
Well, in the Rothschild and Stiglitz, you get a unique one because I know that's the only one. But for example, we know that the Akerlof supply and demand curves could just cross in 3 points, and then there's 3 equilibria. Which is interesting. But let me just do the intermediate micro of this, and then I'll kind of have a broader discussion because I'm kind of closing my eyes to a lot of issues and just pretending that I'm giving a typical presentation. So let's say the marginal costs of providing yeah.
We should define inefficient. I did on the previous slide, because people talk about different notions
Yeah.
of efficiency here, like there's constrained efficiency versus the.
Yeah, so what I want to do now is that I want to do the intermediate micro of this. So I'm going to call efficiency just adding up dollar benefits to everyone measured in dollar terms. So social welfare, as opposed to looking for a Pareto optimal and so on, which is actually interesting too.
Versus if you could force people to buy that drug at less.
Sorry?
Inefficient versus what?
Inefficient versus, I'll compare what's the first best if I could force everyone to purchase insurance. I'll show why there's a gap from that. And I'll show you why even simple policies can get us closer to that.
Why that relative to constrained efficiency? This is also constrained
Yeah,
efficiency.
yeah. So both are interesting. I think this one's more policy relevant. So I guess that's why I try to explain this one first, if I have to explain one. But both are. You can do Pareto optimal regulations and so on. But anyway, so in a nutshell, so here's why this is inefficient. So let's say that I take one person, Mr. Theta, and Mr. Theta is choosing how much insurance to buy. So Mr. Theta is going to look at his marginal utility, the derivative of his utility with respect to coverage. And Mr. Theta is going to look at P prime, which is the derivative of prices, what's the price of additional coverage. And he's going to purchase his equilibrium quantity where the two are the same. Now, that's not efficient because Mr. Theta's marginal cost, because of adverse selection, could be anything. And so, in this case, Mr. Theta bought too little insurance because his marginal cost was lower than P prime. And moreover, even if I take all the people who are purchasing the same contract, if there's multidimensional heterogeneity, they're going to have different marginal cost curves. So, these are marginal cost curves of everyone who's purchasing the same contract. So there's kind of two inefficiencies. One is that even on average, marginal cost is going to be lower than the derivative of prices because prices go up both because of marginal costs and because of selection. So there's going to be this number SI, which is an important number that tells you the difference between these two curves. And there's going to be variation in the marginal cost of anyone who's purchasing that contract. So it turns out that I could have used some tools similar to public finance that would tell me what optimal regulations would be in this very stark setting. And they would tell me things like, I actually want to give subsidies in the intensive margin that compensate for selection. And I want to also try to adjust this in a way that if people are heterogeneous in their elasticities, I might want to try to get the higher cost people to purchase less insurance and so on. So I'm not going to go into details of these formulas, but I could go back to my mandate example, and this looks clearly suboptimal, and indeed it is suboptimal. I could calculate what the optimal policy would be, and it would involve giving a lot of subsidies in intensive margin so that I wouldn't have those big lumps there. So I'm done, and I'm opening for questions, but I guess my conclusion would be that we can use price theory to think about this. I think one point that I want to discuss in the questions is, wouldn't there be other reasonable ways of also figuring out what happens in this, in this markets? And I think there are, and I want to talk about that. But I want to talk about some. I guess I will talk about the open problems in the end. So maybe let's just discuss first. Yeah. So people seem to be itching themselves. So I'll welcome a few questions and then try to.
The single dimension, so the result you didn't talk about was that you can motivate it with this per trend competition game.
Mm-hmm.
And unless I'm mistaken, that has to be over just the single dimension, right? Because otherwise, if you allowed for competition over two dimensions, like premium and deductible in the Rothschild-Siemens case, you would then open yourself up to the same competitive pressures that break the equilibrium. So
yeah.
am I right in thinking that that's where the single dimensionality
in the Bertrand game? Yeah. So Nathan's talking about a result that I didn't present, which is that you could say, look, there's this price taken equilibrium notion, but maybe let me go back to the theory picture, I guess. So there's this price taken equilibrium notion, but we know there's not a Nash equilibrium necessarily, because some firm could go and offer a contract here. They could offer full insurance at a lower price, get everyone, and they would make money, and this wouldn't be a Nash equilibrium. And we know that happens all the time because of this Riley result. So what we do in this paper is that besides, given this more price-taken explanations and game theoretic in the sense of the refinement literature explanation of why this is reasonable, we also kind of reverse engineered a strategic game that has this as an equilibrium. Now, I reverse engineered a strategic game that has a lot of assumptions. So the way that my strategic game worked to make this be an equilibrium, and it makes sense that I had to put some crazy combination of assumptions, because a lot of smart people have spent a lot of time trying to get something reasonable to come out as an equilibrium, and we got something reasonable to come out of an equilibrium in these much broader cases that before we didn't even have a guess of what a reasonable prediction would be. So the assumptions are, there's a lot of firms that each one offers one contract. And in each contract, there's actually a lot of firms offering the same contract. They're slightly differentiated. And each firm has a capacity constraint. So they can't just go and take over the entire market. So in that model, what makes it so that you can get an equilibrium, a strategic Nash equilibrium, is that nobody can go and offer this really low-priced contract because they can't go and take the whole market. Yeah. But there's a lot of things playing into that. So yeah.
Could you have motivated this with the Riley game? That's what I'm trying to.
I don't think so. I think basically everything that all of these pseudo games are just so specific that if you actually want to motivate it in a way that it's going to work here, then all sorts of things go wrong.
Right.
So even
but it would be interesting to figure that out. Yeah, Yonko.
even with the strategic foundation that you have in mind,
Yeah.
I'm wondering, right, I mean, there are a small number of firms who will start making money by offering these pooling contracts, right, that normally break the...
So you're saying it could be that all firms at the same time change to here?
No, not necessarily. So over time, I mean,
Yeah.
gradually more and more firms find it sort of profitable to offer contracts like that.
You mean in a dynamic
Even with
game?
Yeah, something like that. Like even with a small capacity, I mean, if it turns out to be an optimal thing to offer contract over there, I mean, why isn't it that this equilibrium is stable?
Yeah, well, it's interesting. I mean, it's too bad that I didn't have my other set of slides.
Mm-hmm.
This is actually related to Xavier Vives's thesis. So if you just look at the firm's first order condition in the when this Bertrand game, then they're actually only going to want to undercut very, just a tiny bit below H. And it's not like all of them are going to flow below. Actually, they're going to have very small markups. They have markups, but they're just very small. Yeah. So here's a tough question that I was hoping someone would ask, because I think this is the more of an elephant in the room than anything else, except I guess if we had a real elephant. So imagine that there's 99% low types and 1% high types. In that case, this would be saying that we still have this as an equilibrium, but that doesn't make much sense, because shouldn't someone try to offer everyone the pooling contract? Why do we have all these low types just getting this? And not only that, but then as you move from 99% to 99.99 to 100%, then suddenly that completely changed what the equilibrium was. So isn't that weird? Isn't everyone worried about this? I'm worried about this. So yeah. So I think this is related to a deeper point, which is that I think this pooling equilibrium, for example, is actually pretty reasonable. Just like I think this one is pretty reasonable too. Probably in more situations more reasonable than the pooling one. And so it's not like we're going to completely settle this debate of what's the right equilibrium notion. I think there could be other equilibrium notions. But the problem is that as we look at this huge literature, all of these equilibrium notions, they only work in these very particular cases. And they're all kind of designed to work in these very particular cases. So that creates a problem, because if you want to compare two equilibrium concepts, it's very hard to tell whether the crazy results are coming because the concept's wrong, or because the model is wrong. We just put bad assumptions in the model. So we could be getting crazy results because we assume that there's only two types, but we could be getting crazy results because because of the equilibrium notion. So it's hard to compare two equilibrium notions if they're only defined in this kind of case. So a similar example is,
so the point you're making right now is that a free variable here is the ratio of highs to lows.
Yeah.
And no matter how you change that variable except setting, say, highs to 0,
yeah,
you're going to get this as the outcome.
Yeah. And that's a little crazy.
Kind of surprising.
Yeah, that's weird.
Well, it's because you're getting the Riley move, right? So if you had full support of the type distribution, Riley gives you no trade, right? That's the, because there's always a desire, this is the...
So Nathan, that is the correct answer for someone who knows this literature in and out. He's just explaining to people what happens in the Riley equilibrium.
Right, so like you had probably arbitrarily close to 1, right? Everything would...
Yeah, let me explain here. So what's weird is that it's both that if you have 99% of L types, then they're getting this really inefficient low insurance, and which is weird. And it's weird also that when you move to 99 to 100, then you completely change that to them getting the efficient level of insurance. Does it make sense? There's two things that are weird here. And so one thing that's interesting is that this particular weirdness is actually not so much a weirdness of the model. It's more of a weirdness of the one-dimensional heterogeneity. So for example, if I go to this example here, it turns out that I tried to change the distribution of types. I tried to change the support of the distribution of types. And sure, the equilibrium is not going to be exactly the same, but the equilibrium is going to change a little bit like we expect that it should. So I'm not saying that this is the only way that you can model this. I think one thing that would be really nice is to have another model that works in this multidimensional setting and where we can have pooling. But then I think it's interesting because then we can compare the predictions of the model and see which ones are telling more about real life and about how these markets work and about the policies that people can do.
But you do have pooling.
Well, yeah, but I mean pooling, you know what I mean.
But the question is like,
cross-subsidization.
Well,
I think it would be interesting to have an alternative model that has cross-subsidization.
But I mean, effectively you do have, in other words, once you get into multidimensional heterogeneity,
everything's pooling, yeah.
Everything is pooling, and there is tons of cross-subsidization just within.
Well, but each contract's breaking even, right?
Yeah.
So it's like I agree.
I'm just saying, like, I want to reinforce what you just said, which is that, like, it may be that these things are really not that different with a lot of rich heterogeneity. Yeah. It may be that the biggest differences between them arises because of these very specific models.
I see.
And like, once you have rich enough heterogeneity, it may be that they actually start being much
You're
more
saying
similar.
once we start looking at models like this, then we're going to remember actually what we were confused about in the first place.
Yeah.
Yeah, that's possible. But I think it would be interesting to develop this kind of model because, I don't want to say this is the only, I think there's 3 plausible reasons why this is a good way to think about public policy. So that one is that I think this captures well the unraveling idea that we think explains this in the one-dimensional case. 2, I think there's this game theoretic refinement logic that we got rid of the pathologies related to measure 0. And 3, we have this very specific, game theoretic foundations for this. But, that's not to say that we shouldn't have other models and try to compare the outcomes of this model with some other model and see which ones explain real life better or help us understand, other aspects
I guess
of public
just
policy.
what I was saying in defense of
Is that in
your
the end it
approach
might be,
is that like before we say, oh, but you could have considered another model, it seems relevant to figure out whether there is another model that's reasonable that gives you something that's all that different in actually reasonable cases, rather than in these extremely specific examples on which all attention has been focused, but which may not actually tell us that much about what happens in realistic cases under any solution concept.
I think this is a related question, but just my own sanity.
By the way, Casey is one of the world experts in this area.
I wish I was.
Just so everybody knows, there's not just some dude who is in the hallway.
So just so I understand sort of the complaint about this oddity is basically a discontinuity at 1 when you put all the weight on the L types, right?
Yeah.
And your response, if I understand it right, is basically saying, yes, there's a discontinuity here, that discontinuity is no good, but the discontinuity is sort of a non-generic feature.
Yeah.
And in lots of other models, there wouldn't be a discontinuity, and somehow it's that we pick this particular model that has the discontinuity, but if we picked a random model from a bigger space, we wouldn't have those discontinuities, which is not where I thought of.
I think what you were saying is that as the distribution changes, the choices changes, right? That's what you see with multidimensional model, but you don't know whether discontinuity disappears.
I know, yeah, I do. I was going to explain that now, actually. Because, given that this is an econ CS seminar, this is actually, I think, a pretty interesting, more mathematically advanced topic. Sorry that I will only explain very simple things. This one's simple too, but I think it's a little more interesting, which is, why is it that, that phenomenon, that weird phenomenon, doesn't actually happen more generally? So here's one way of thinking about it. So let's say that this is the set of all possible prices, and then this is the set of all possible perturbations that I can do, those measures of behavioral guys that I could add. So I can look at the points in this plane where the profits of the firms are 0. So, so like in this, if I have no perturbation, there's going to be some points where profits are 0, the equilibria. But there's also going to be points where the profits are 0, which are not equilibria. It's just because nobody's buying anything. So, so sometimes you get a bunch of points here where profits are also 0. Does it make sense? But then the thing is that if you try to draw in the entire space what this looked like, then actually this is not the equilibria, right? This would be the weak equilibria. But if I try to draw this in the entire space, then it turns out that this actually looks something like this. And so once you figure that out, then it's and this is actually kind of like under certain assumptions is kind of a nice surface. And so basic differential topology actually tells you that that thing doesn't happen all the time. That thing only very rarely happens.
So, but that thing, I mean, there are two things going on. One is that the outcome, equilibrium outcome, is completely invariant with the change in distribution. The other thing
that's not going to happen all the time.
And then the other thing is there's a discontinuity at the.
That's also not going to happen generically. Yeah. So I mean, I just want to, I guess, say some open questions that I think are interesting, since there's a lot of PhD students here. And I guess I was in grad school not that long ago. And I think one thing that's really cool with our interaction with computer scientists is problems that I think are productive for us to work together. So if we have time, I'll be happy to discuss more, but I just wanted to talk about these. So
and can I just give one more reason why I think that the discontinuity, like why the reason that the discontinuity doesn't really make sense, that it should exist? Not, like,
it exists in knife edge cases.
No, I know, but the reason why you wouldn't think so. Suppose that in a world of multidimensional heterogeneity or any sort of realistic world, it's just not going to be the case that there's going to be no one who is healthy who's going to buy the high amount of insurance. Like, we see all the time that there are healthy people who buy a large amount of insurance, like even if it's really highly priced. And there's quite a lot of evidence that people do these behavioral things that we were talking about before. They buy a lot of insurance even though it's irrational for them to do it. That just happens a lot. And so if there's this high amount of insurance being offered and we're reducing the number of the high types, like, it's going to start getting priced as if it's mostly the low type people who are, taking it up, which is true. So, I mean, that's the way I think about it.
I think Nathan's
Can
going
I
to
give you a
disagree.
counter-argument? So, the world, I'm totally on board, like, the idea that there's, like, multidimensional heterogeneity. Some people have preferences for, say, let's take life insurance as an example. Some people, like, want to move money to the state of the world when they die. Other people, like, want to actually have things maybe go the other way. Sorry. So, the issue is, as you get, what's going to, like, make the equilibrium start to look a little nutty is, imagine you're the insurance company and you think there's a 1 in a billion chance the guy who's looking to buy your contract is going to, like, already knows that, like, death is not going to happen. The Grim Reaper has shown up, right? Whether that's 0 or whether that's 1 in a billion, like, sure, put on multidimensional heterogeneity, but for the guy who's got the probability close to 1, the rest of it is just not relevant for demand, right? And this equilibrium prediction would be that the existence of whether or not there was the 1 in a billion guy, he could shut down the entirety of the market here.
But that's not
And
true.
that's
That's what we just said.
That's what?
That's not true. That's only true.
It is true.
No,
No, it's not true.
Okay,
What am I
so
missing?
I don't think that is true. I think that if you price it at a reasonable level,
We're in a binary world, right? You die or you don't die.
well, I'm not in a binary world. What I'm trying to say is, like,
Life insurance is a
you're saying
binary
you're
contract.
just saying that.
No, life insurance, the only reason why the companies make money is because people surrender the policies too often. So it's not binary. But anyway,
I mean,
but let's say it's binary.
I
Even it's binary.
I completely agree that you cannot base
Yeah.
our judgment about which equilibrium makes more sense just based on the Rothschild-Stiglitz model.
Yeah.
But that's one good benchmark, and
Yeah.
there are two compelling predictions. One consistent with Riley,
Yeah.
the other consistent
Miyazaki,
with
yeah.
Wilson, for
Yeah.
instance, right? I mean, so but then as the proportion of the low type gets very very close to 1,
Yeah.
at some point it starts to make this
The
second one
Miyazaki
makes a
would
lot
make
of
more
sense,
sense.
right?
Yeah. So that's why I think it would be interesting to, like, in a multidimensional setting, be able to compare both and see which one kind of makes more sense.
Nathan, I mean, there is a coherent, simple answer under what I said to what you were saying. And I just wanted to explain that. So, like, if I offer a contract that offers a lot of insurance, under my version of multidimensional heterogeneity, as long as there's only a very, 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 very small chance of that person who absolutely knows that they're sick existing, and there are still a reasonable number of people who just, for whatever reason, are impelled to buy a high degree of insurance, then as the number of people who are these really sick people gets really, really small, most of the people who take that thing up are the crazy people who just feel like they want to buy insurance but aren't super, super sick. And on the other hand, if there's a substantial number of people who are super, super sick, then that will be a problem because they'll swamp the crazy people who just feel like they want to buy insurance. Now, you don't have to buy into my assumption that there are people who just feel really impelled to buy more insurance, but I think that's a reasonable thing to think about the
But
world.
I don't see that as the prediction of this model. I see, maybe I'm misinterpreting your story. What I see the story is you've got two-dimensional types. You've got I'm going to put it in the binary world. I agree that, like, the world is not binary, right? But I think it's reasonable to sort of, this firm decide whether or not to sell an insurance contract. They're moving money across some state of the world. And so I think a model that doesn't satisfy what you want it to satisfy in a binary world, it's hard to say, well, let's just go to more dimensions and then fix the problem. And maybe there is some interesting convergence thing there, but in the binary world, I'm thinking there's P's and there's U's and there's heterogeneity in U's, so you've got these two-dimensional things.
Yes.
The argument that I'm making is as P goes to 1, like, U doesn't matter much anymore for demand. And that's going to impose this incentive constraint that you're going to have to subsidize that guy, and we know in this equilibrium you're not going to subsidize that guy, so you're going to shut down the whole market.
I'm not really following what you're saying.
I mean, there are cases where you shut down the whole market. I think that's fine. But it's not. But it's like you can't by changing the support. So imagine the Akerlof. Just imagine the Akerlof model. You know, we have demand and average cost.
Yeah.
By changing, you know, this last guy, you could do something like doing this. You know, you can shut down, you can create an equilibrium that shuts down the market just by changing a little bit things. But you can't ever change, you know, that this other equilibrium exists too.
But you could if you, so that's in the world where you restricted the contract set, right? This is the.
That's the one that we restricted.
In the Rothschild-Stiglitz world, you shut down, you get the Riley equilibrium back and you shut down the whole thing, right?
But that only works.
I propose that we
Yeah, we can
Okay.
call three
next
minutes.
to go through open problems and then.
Okay. Well, I mean, I'll just use 1 minute, I guess. So I think one interesting open problem is that there's a lot of assumptions in this Bertrand convergence result. And so it would be interesting to kind of like look at how we can weaken the assumptions. So for example, I talked to you guys about a case where each firm only offers one contract and sets a price, but I'm pretty sure that you could have firms offering menus of contracts and things like that. And there's some less technical questions that I think are interesting, which is like, look, you know, if we have this one model that always gives you an equilibrium, then maybe we can start with questions about real life, about how these markets work, and find interesting models with closed form solutions that help us think about it. So, you know, because it's so new, it's actually super unexplored. So Victor Luz from UBC and Piero Gottardi from the European Institute have some interesting work on this. And then I think another set of open questions it would be to come up with other solution concepts. So for example, Nate, you know, thinks that there should be a lot of cross-subsidization across contracts. And I think maybe, and I think, you know, I think we should have models of that too and then kind of compare their predictions. Yeah, and I think it maybe, you know, I guess this question of, you know, it seems like I thought this question was simple of, you know, the whole, but isn't it the case that if you start from this model, you could slightly change the distribution of guys in the tail and completely change the predictions? And the answer is that you can't. But, you know, I guess, you know, maybe more people could build on to my differential topology results that haven't posted on the internet yet. And I think that's an interesting problem to work on. So thank you very much for your attention. It was a lovely discussion.